Okay, so good morning, everybody. We are on the week 9 of the process modeling, basically. Okay, where we only have about 4 times meeting again. Generally, as we go into the end of the semesters, I will not go and spoon feed you with more materials, because I think by this time already it's not very efficient to spoon feed you with all the materials, but rather because I only have one lecture every week with you on the process modeling for the last 4 weeks. We will just try to cover the remaining materials, which is the steady state distributed model and the transient distributed model. To the other lecture time, you can utilize it for working together with your group mates on your project 2. Okay, or likewise, you can also do it for your the other assessments that are due, for example, like the project 1 in process control, or if you get an extension, your laboratory report for your process control. Because I think you deserve much more time to work to concentrate on your project, on your group project. Okay, so far I hope you maintain your close communications with your group member. And then for your project 2, like I mentioned before, it's the project 2 problem has been distributed, so you need to start working on the project 2, because we have a quite tight timeline. For project 1, I think most of you get very, I would say, very good mark this year round, I think. Okay, so if I go into the week 9 materials on the process modeling and optimizations, we continue on the finite difference method, right? Last week we talked about the shooting method, where we basically go through the algorithm and how we apply the shooting method into the problem. Let's say if you have something, a property that is known in the end instead of the beginning, meaning that that is no longer an initial value problem. What you have is basically something that lies at the end. And what you need to do is you need to basically start with an initial guess. Okay. After you start with the initial guess, then you solve the problem, and then later you see whether the value at the end will match your boundary conditions or not at that particular position. So essentially, it becomes a nonlinear problem where you need to use a residual, and then you can use another toolbox in MATLAB, such as the F0, to solve to make sure that you have a zero difference between the boundary between the property at the property value at the boundary conditions. Okay, that's basically what we showed in the MATLAB code. So in the finite difference method in here, for today's, we talk about the steady state distributed model. So meaning for the steady state distributed model, there is no variations with respect to time. I noticed in your project 1, when I evaluate your mark, you did not, some are very some are confused with the steady state, with the steady state and the transient, and then with the LAM model and the distributed model. So I think it's probably a bit difficult if I expect you to understand this in one unit only. But as you go with the more examples, it's very good that you know what is the problem that you have at your hand. So if, for example, you are dealing with the steady state, then it's very important that you know that your property does not vary with time. If you are dealing with the transient model, your property vary with time. For LAM model, you don't have basically a variations of your property with respect to the position. So everything in the system that you are interested with is the same, the property. So there is no variations with the position or the coordinate. Whereas distributed model, you have a variations of the property with coordinate. So if I go and talk about the steady state distributed model, meaning that I may have a variations in the property with respect to one or two coordinates. In process control, for example, when we are talking about the dynamics, then obviously we talk about the variations with time. So for everything that we discuss in the process control, the model will be transient or unsteady state law model, or it can also be a transient or unsteady state distributed model. But the one that we cover in our process control is the simplest problem. So it's only the transient law model. Okay. So it's very important because later on, if you try to solve the steady state law model, transient law model, or you try to solve a steady state distributed model, or you try to solve the transient distributed model, then the numerical methods will be totally different, right? So it's very important that you really know which among the model classifications that you have with, and that's why in the process modeling, I give you a material that is based, the coverage of the material is based on the different models. So we split based on the steady state and then transient, and we also split between the lump and the distributed model. So no matter later if you go into whatever problem that you want to solve as a chemical engineer, or later if you go and do your postgrad, you probably go into the modeling and simulation area or transfer phenomena. Then the way that you classify your numerical method will be based on this classification. Okay, of course, we have something else again that we call a stochastic model. So in the stochastic model, meaning we put in a probability into our model as well, but that will not be covered in our process modeling, because that will make it much more bigger again. Because if we start putting the stochastic model, we start dealing with the statistical analysis as well. Okay, so that area is better left to Dr. Hao or Dr. Vignesh, who knows much more about this model. So it belongs to an area that we call a process optimization. So this probabilistic, when you start on putting into this kind of things, then you will be dealing with the statistical, where how many chances that this will happen, how many chances that will happen. Okay. So if we go back again to the finite difference method, then we want to solve it for a boundary value problem. So how does this method work? This method works by dividing the space dimension into a set of mesh points. So the derivative will be approximated as the difference between the mesh points. So the approximation basically replaces the differential equation, such that you obtain one equation for each mesh point. So the thing in here is basically you convert the differential equations to become a algebraic system. So for example, we choose a mesh on the interval. So you start from point of A, and then you end at the point of B. So you take many points from 0 to n plus 1, such that this point xo, x1, x2, and so forth until xn plus 1 lies in between A and B. So as a result, the mesh has n internal grid points. So if I put it like this, okay, into your additional materials, is basically creating points like this. Okay, from 0 to 4, you are creating an internal grid points 1, 2, 3, something like this. Okay, you're creating points like this. So meaning that your step size will be b minus a divided by n plus 1. So that you have this kind of relationship that connects the point of xi plus 1 with xi. We approximate the derivative. One of the most accurate way of converting or approximating the derivative will be to use a centered difference approximation. which is this one. Xi plus 1 minus xi minus 1 divided by 2h. So dx over dz is equal to this one basically. So if we have n and basically n points, right, and integral grid points, then we converted each of the differential equations into this. As a result, we will have n equations. So there is one group that get the center difference approximation. So the error that we get from the center difference approximations, or the error that we get from the forward difference approximation or the backward difference approximations will be different. So the error from the center difference approximations will be less compared to the forward or the backward difference, because you can check it using a Taylor expansion. Okay, I will not discuss it in here because this will be a little bit outside of the scope that I give today. But if you are interested to find the error, then you can go into the book of Dorfman. It's explained in that book very well for that particular example. So note that we may have a point outside the interval like x minus 1 or xn plus 2. So if I put it in here, we have this kind of point x. This point is called minus 1. Or this point, for example, I put it in red in here, is the point that is outside of these 4 points. 0, 1, 2, 3. We have 4 points. This one. Okay. Then we apply the approximation also to the boundary conditions. Because the approximation is applied to the boundary condition, this method is called method of the fictitious points. Because those points are actually does not actually exist in the real system, but they are applied irrespectively to facilitate the solution of the problem. Once we get that thing, then once we do that thing, then we will be able to solve the algebraic equation system. Okay, so if the ODEs and the boundary conditions are linear, then the equation system becomes linear and can be solved using Gaussian elimination. If the ODE and BC are nonlinear, then the equation system will become nonlinear and will require a nonlinear solver like a Newton method. Okay, so these are the details into the center difference approximation. Okay, so this one in here is probably forward approximation. This one is probably the backward approximation. The details you need to check again because I think they are defined a bit differently. Okay, if I go back in here, probably it's defined or not. I'm not too sure. I don't think I have it in here. But one is forward, the other one is backward. So the center difference approximation is called as a second order approximation because you are basically averaging the forward and the backward difference approximation. So that's why the center difference approximations will have lower error compared to the forward or the backward differences. Okay, then the second order derivative can also be approximated using a second order approximation, which means that the second order derivative will be equal to this term in here. Okay, so let's go with some of the example in here. Okay, we're gonna discuss a simple example. So we talk about the tubular reactor with dispersion. The first one that we did in here, for example, if we take 2 internal points, this one will be the first point. This is the end points. So we put 2 points in here. Okay. So the mesh size will become this. Let's say we want to solve it from 0 up to 0.35. So the mesh size will become 0.35 divided by 3 in here. So when you go into the systems and you imagine how it looks like, then it will look like this. And you can connect it also with this with the additional materials that I give you here. Okay. So the center difference of the first derivative will become this. It will have this form. The second derivative will have this particular form. Now then what you do is you apply the discretization on your equation. So you converted this ODE with the central difference approximation with this one. This one you modify with this term in here. Okay. Then your C in here will become CI. Then you can do some manipulations of your term. Basically, you move this D into the left-hand side, and then oh no, you move this V into the right-hand side, basically. Okay, so it becomes negative in here. Then you do it for the 4 points in here, right? You do it for 0, 1, 2, 3, 4. So you basically do it for this particular point 0, 1, 2, and 3. You basically substitute 0 into this particular equation. You substitute 1 into this particular equations. You substitute 2 into this particular equations. You substitute 3 into this particular equation. So you have 4 different equations, basically. Okay. And then we also need to convert the boundary conditions as well. Don't forget that we need to convert the boundary conditions also. So you can go through yourself into these derivations that I showed in here. Basically, the final form that we will use to solve this particular problem is this particular form here. Okay. So you have this can be converted into 4 equations in here that is expressed by here. So this B0 in here will be equal to this. This B3 is equal to this. However, your C minus 1 and C4 in here is not really known. So you basically need to convert this boundary condition into something that is known, and C4 as well. Right? Apply your discretizations on the boundary conditions. You have 2 boundary conditions, this first boundary conditions and the second boundary conditions. So you do it in the same way with your center difference approximation. You just change this particular term with their different finite difference form. The same one, this one also change with this center difference approximation form. Note that this one lies at the beginning, so your I will be equal to 0. This one is supposed to be put at the end, so your I equal 3. Right? So once you do that thing, you can then find out your C minus 1 in terms of something that is known, and your C4 will be equal to the C2. When you ask me again, why is it like that? Then this will be why it is like that. Okay, so you go and check in here. So after you convert it to this one, then you will be able to find out this C minus 1 with respect to the other term in here. So this will be going to here. Okay, as a result, you will get this one. Okay, this one, if you substitute I equal 3, it will be equal to this. So as a result, your C4 will be equal to C2. These boundary conditions you substitute into your original equations in here for each of the grid. Okay, then you know that this will affect your first equations, I equals 0 and I equals 0. Okay, as a result, this is something that you will get for your first equations in here. This I at equal 1 does not change. This one does not change. Your I equal 3 probably will change because your C4 will be equal to the C2. So this is basically the overall of the matrix that you will get. But we don't need to solve it using this. We can also solve it using this particular form as well. So this is what essentially happened after we substitute the C minus 1. We will have this overall matrix. Okay, this one is called A2. This one is called A1. This one is called A0, and this one is called B. This matrix can be coded into MATLAB. Okay, these d vector elements in here, D0 is equal to this particular form in here. Okay. Then if you put everything into the single linear algebraic equations, you will have this big matrix in here. This is what you call AODE. This is what you call B. Your unknown is C0, C1, C2, and C3 because you need to know the concentration at this particular point. 1, 2, 3, 4. What are these concentration at this particular point in here? That's what you need to know, right? Basically, so you have a matrix. Basically, the number. You remember in the first in the second lecture, the square matrix give you a unique problem solution because the number of your variables will be equal to the number of the equations. So you have 4 equations, right? 1, 2, 3, 4. At the same time, you also have 4 unknown variables that you try to solve. Therefore, you will be able to solve your C0, C1, C2, and C3. Okay, so basically without going into the details, I think you guys already have a training on the MATLAB codes as well. Right? What you need to do is just make substitute all the parameters, and then you need to make the matrix for A2, A1, and not. Okay, and then specify specific component in your matrix to get this particular variables, the big one. Okay, then you will be able to calculate your AODE as long as your B. Then you left divided AODE with B to get your C. So this is what happens if you use 2 internal points. This is what happens if you use 100 internal points. So the code is made such that you don't really have to just use 2 internal points. You can choose to use also 100 internal points if you want. If you plot like this, then you will have, you know that of course if you use 100 points, then you will get a very smooth profile in here. But in general, the trend will be the same. Okay, so you basically can solve the concentration from 0 to 0.35. So if we use a shooting method, the algorithm will be more complicated. But if you use a finite difference, you can see that you can solve the same problem, but the method will be much easier in here. So you can compare the method that you solve using your shooting method with the method that you solve using a finite difference method in here. So which one do you want to choose, for example? That's up to you entirely. Engineering is the same like that. You cannot really say something is very good until, because there are many different pathways for you to solve a particular problem. So probably the valid comparisons will be to compare the computational time that you need for solving this with the computational time that you need to solve using the shooting method. You can see, right, in here clearly that that the slope at this particular point at the end will be equal to 0 in here, which will become apparent to you if you go back into the slide from last week. Okay. Okay, now we go to another example. So this one is the example 2, nonlinear tubular reactor with dispersion. So you can apply the same steps again. Okay. The difference is that you have your reaction in here is a second order reactions. Okay. So you do the same thing again. Everything is the same. Then the final matrix will become like this. So probably you can go into my additional materials in here to check to see. So this one, as you can see, this one is the second order in here, right? And then if you put in the simplest case where you use 2 internal grid points, so you have 4 different equations. And then this one is basically showing you the conversions of the boundary conditions. If we substitute the boundary conditions, we will have these final equations in here. Okay. The one that are affected is the first one and the last one in here. Then as a result, you will have this particular matrix in here. Okay. this will be the thing that you need to code into your MATLAB. So this will be what you have. Now the thing that you have in here is you have to use a nonlinear equations in here because you have that that term that makes it nonlinear in here. Okay, so this is what you did. You just define the matrix in here. Then you solve using an fsolve in here to get the value of the C that will make this residual to become equal to 0. If we do that thing, then we will get this particular terms in here. And if we do it using a finite difference method, we don't have to use the different coordinates to make the solution stable. This becomes a very simple matrix problem that you can solve using a nonlinear toolbox in here. Okay, so everybody has any questions up to this particular point? You get more confused, or you are okay with all the explanation that I give today? Alvin, Amanda, Clarence, Daniel, James, Jason, Chising, Michael, Taha, Rachel, Selena, Sakya, Tiffany, Yusi, Wong Yo, Weising. Is it clear? Everything is been given already. The solutions. You can go and refer into the additional material. So nothing is mysterious. So you just have to. If you really want to understand this, then you just have to go and derive by yourself. So that's what we did in here. So we go through and derive everything, and then also the same with the other example that we are adding in here. We are also putting in all the things and solve the particular problem. That will only be clear if you go through and try the derivations by yourself. Okay, guys, if there is nothing else again, then there will be I will not utilize, as you know, from this point onward, I will not use the second lecture because you only have roughly 4 weeks. Probably after this week, that will be 3 weeks. So you just concentrate on your project 2. And then for your take-home assignment 2, go through the examples that are given on your process modeling slides. You may want to pay attention on the derivations of some of the distributed model, on the derivations of some of the numerical methods, for example, bisections, something like that, or the linear regula falsi, for example, or the Newton-Raphsons. So we may want to test your understanding if you do the calculations manually, how you do that thing for a particular problem, or it may come out something like a Euler method or the Range-Kutta method. Something is basically just to test your understanding whether you really understand those numerical methods or not. So in essence, this modeling and optimization is a very wide subject, meaning that I have to cover so many models from the beginning until the end. At the same time, I also have to cover the numerical methods. And at the same time, I also have to cover the 2 software to give you introductions or a feeling of how MATLAB is working and also how Aspen HYSYS is working. So this modeling and probably control, if it is given properly, then it should be something that are quite tough as well, because you need to be able to be equipped with the tools to simulate your control structure. So far, are you okay with the Aspen Plus dynamics that you get from Hannah last week? I'll stop my recording in here first, okay?